Students, we will discuss about the performance study on an axial flow fan and a centrifugal blower in this session. This photograph shows the setup used to find the performance of a performance of an axial flow fan. A fan is running inside the tube. The fan is run by a motor, which is more clearly shown here. This is the tube in which a fan is rotating. The fan is run by an electric motor, which is shown at the other end. We use two pitot static tube to measure the velocity of the air inside the tube, one at the suction side and one at the delivery side. The schematic sketch of the setup is shown in this figure. The fan is rotating inside the tube whose diameter is d. When the fan is rotating, the air is sucked inside and air is delivered to the other end of the tube. The pitot static tube is used to measure the velocity of the air at the suction side and at the delivery side. The pressure of air we have to measure before the fan and after the fan. So the section 2 or the stage 2 is the stage which is before the fan, and stage 3 is the stage after the fan. The pressure of air is not constant across the stage 2. It varies from tip to hub. So we have to find the average of the pressure at stage 2. You have to find a pressure at tip, that is called 2T, and the pressure at hub, 2H. Find the average of these two. So that is the pressure prevailing before the fan. Similarly, at stage 3, we have to find the pressure, one at tip and one at hub. We have to find the average of these two, that is the pressure prevailing after the fan. In order to find the pressure at these 4 points, pressure tapping points are inserted and the tubes are connected from this pressure tapping point, and the tubes are connected to the manometer bank, which is shown in this photograph. So the 2T, the tube connected to the pressure tapping point 2T is connected here, and 2H, 3T, 3H are connected with the corresponding tubes, manometric banks, as shown in this figure. Now we have to record the pressure at 2T, 2H, 3T, 3H using the manometer reading. The manometer contains water as the manometric fluid. So we have to record these 4 readings in terms of centimeter of water column. As I already told you, the average of the pressure prevailing at stage 2 we have to find out. So average of 2T and 2H we have to find. That's the reason why we are dividing with 2. Similarly, we have to find the pressure at 3T and 3H. Find the average of these two pressure by adding and divided by 2. So the average of pressure at stage 2 minus average of pressure at stage 3, that gives the pressure rise across the fan in terms of height of water column. Since we measure the pressure in centimeter of water column, dividing this reading by 100 will give the pressure rise across the fan in terms of meter of water column. We have to convert this pressure found out in meter of water column into meter of air column using this formula. So static pressure is given by rho GH of water column, which is equal to rho GH of air column. Since we want to find the pressure in terms of air column, we are taking this H of air to the left side, and this is given by rho of water, H of water by rho of air. So this is how we are going to find the head of air using this 4 manometer banks. To find the discharge of air, we are using the formula Q is equal to area into velocity, where area is the area of the tube in which the fan rotates. So pi d square by 4, where d is the diameter of the tube, and velocity is measured using pitot static probe, which is fitted at the suction side of the tube, which is given by square root of rho m by rho minus 1 into 2 GH. So H is the reading of the manometer which is fitted with the pitot static tube. So since water is used in this manometer also, so H is measured and substituted here in terms of meter of water column, and rho m is the density of the water, since the water is the manometric fluid, and rho is the density of the flowing fluid, which is air here, and this gives discharge in meter cube per second. Once you know the head of air and discharge of air, we can find the output power of the fan as WQH, where W is the specific height of air, Q is the discharge, and H is the head of air. The input power of the fan is found out using this formula, 3600 into N into eta m divided by T into EMC. And efficiency is ultimately found out as the ratio between output power by input power. Next, we are going to discuss about how to find the efficiency of a centrifugal blower. So this photograph shows a centrifugal blower setup. The blower is running inside the casing. The blower is run by a motor. The impeller is run by a motor. The impeller is rotating inside the casing. When the impeller is rotating, the air is sucked through this opening and it is delivered through this pipeline. So we have to find the efficiency of the blower. For finding the efficiency of the blower, we need to find the output power, we need to find the input power. So for finding the output power, we have to measure the discharge and we have to measure the pressure rise. For measuring the discharge, we have fitted a orifice meter along this tube. So it is shown here. The orifice meter which is fitted along the tube is shown bigger here. So this is the orifice meter fitted. This orifice meter has got an opening whose diameter is D2. And the pipeline through which orifice meter is fitted has diameter D1. So with the help of D1, D2, we can find the area at 1 and area at 2. To find the pressure of air flowing through the pipeline, a pressure tapping is fitted, and this pressure tapping is connected with a U-tube manometer. So this is the U-tube manometer that is used to measure the pressure rise of the due to the action of the blower. So this manometer has got one end fitted with the pressure tapping point here. The other end is open to atmosphere. Since water is used as the manometric fluid, the pressure rise across the blower is measured in terms of height of water column, HW. And we have to measure the pressure differential across the orifice meter to find the discharge. So the two pressure tapping points are fitted, one at the before the orifice meter, one after the orifice meter. That is shown here. These are the two pressure tapping points which is fitted. So these two tubes are taken to the U-tube manometer to measure the discharge. So this is the U-tube manometer. Both the ends are connected to the end of the pressure tapping point, which is fitted across the orifice meter. So here also, what is used as the manometric fluid, we measure the pressure rise, pressure difference across the orifice meter in terms of height of water column H. So H is the pressure level difference of manometric fluid, which is used to measure the discharge. So once the readings are noted, the discharge can be found out using this formula, CD into A1 A2 square root of A1 squared minus A2 squared into square root of rho m by rho minus 1 into 2 GH. So A1 A2 are the area of the orifice meter opening, that is A2, and A1 is the area of the pipe through which the orifice meter is fitted, and rho m is the density of the manometric fluid, which is water here, and rho is the density of the flowing fluid, which is air. H is the level difference of manometric fluid across the two ends of the manometer used for measuring the discharge. Then the pressure rise is measured using this formula. So pressure can be measured using any fluid column, rho GH of air column or rho GH of water column. Since we measure the pressure in terms of water column, we have to convert this water column into air column using this formula. So H of air is given by rho of water, H of water divided by rho of air. The output power of the blower is given by WQH, where W is the specific weight of air, Q is the discharge, and H is the head of air. The input power of the blower is given by 3600 into N into eta m divided by T into EMC. The efficiency of the blower is the ratio between output power by input power. Thank you. A valve is fitted along this pipeline to change the discharge of the air flowing through the pipeline. The valve can be kept fully open, half open, 3/4 open, or quarter open. After completing the experiment, these are the graphs that can be drawn to analyze the performance of the fan as well as blower. Discharge versus static pressure rise, discharge versus input power, discharge versus efficiency.